folks, welcome to 4.1 Related Rates, Part 2. So in this section, we're going to go through a few more examples, and these are kind of long problems, so it'll take us a while. But I tried to pick problems that were going to be pretty common problems that you'll see a lot, or strategies that you can use for more than one problem. Okay, so let's get started with example 3. We have a 10-foot ladder that is leaning against a wall. If the top of the ladder slides down the wall at a rate of 2 feet per second, how fast is the bottom moving along the ground when the bottom of the ladder is 5 feet from the wall? So I'm going to go ahead and redraw this diagram so that I can label it a little bit more clearly for myself. So I've got the wall, the ground, and I'm going to go ahead and put the ladder in here. Now we know from the problem that the ladder, and I'm going to call this Z, side Z, is 10 feet long. And I also know that the distance from the wall to the bottom of the ladder is, and we'll call that X because it's horizontal, is 5 feet. Now, what else does this problem tell us? It says the top of the ladder slides down the wall at a rate of 2 feet per second. And so what I know from that is I don't know how big or how tall the ladder is right now on the wall, but I do know that that distance, dy dt, is shrinking by -2. Okay. So I've got all of this information, and what I want to find is how fast the bottom moving along the ground. So what I want to find is what is my dx dt, or how is x changing over time. And so when I look at this diagram, I notice that I've got, hopefully, a right triangle. Hopefully the construction folks built the building correctly, and you've got a right angle there. And I've got all 3 sides of a triangle. And so what I'm going to do is think, oh gosh, maybe I could use my Pythagorean theorem. And we know the Pythagorean theorem to be x squared plus y squared equals z squared, where x and y are the legs of the triangle and z is the hypotenuse. And just like we did in the part 1 of the video, we're going to go ahead and take the derivative. So the derivative of x squared is going to give me 2x, but because I'm looking at how everything's changing over time, it's like chain rule. I need to have my dx dt. Now I'm going to add the derivative of y squared, which is going to be 2y dy dt, and then the derivative of z squared is 2z dz dt. Now we tend to do a lot of these kinds of problems, and one thing that I notice is every time I take this derivative that I have a 2, a 2, and a 2. So to make my calculations a little smaller, I'm going to go ahead and divide the whole equation by 2. So I'll get x dx dt plus y dy dt equals z dz dt. I would say this step is optional. I like to do it because it has fewer numbers, but you don't have to, okay? Now I'm going to try and fill in the numbers and see what I have, see what I'm still missing. So I know that my z is 10 feet, so I can put 10 in for z. I also know that x is 5 feet, so everywhere I see an x, I can put a 5. I also know that dy dt is -2, so everywhere I see a dy dt, I can put a -2. But I have a few things that I don't know. For example, I don't know how big y is, so maybe we should find that. And I also don't know what dz dt is, so I should probably find that, because all of that will help me find my dx dt, which is what I'm looking for, okay? So I need to find y, and I need to find dz dt before I can use this formula. So I'm going to do that work off to the side. So if I look back at the initial triangle, I know that x squared plus y squared equals z squared. And I know that x is 5, and y I don't know, and z is 10. So 25 plus y squared equals 100, or y equals the square root of 75. And I'm actually going to go ahead and write that as 5 root 3. And that represents how tall the ladder is up against the wall. So I found my y, and I can plug that into my equation down here. The only thing I don't know that I need is my dz dt. And so the dz dt in this case is how much is the ladder changing. And we hope that the ladder's not changing in length. It's just sliding down the wall. It's just moving, but the length itself is not changing. So we can say that dz dt equals 0. Okay? So if you ever have something that's not changing, you can say that the rate is going to be 0. Okay, let's go ahead and plug in all these numbers then. I've got 5 dx dt plus 5 root 3 times negative 2 equals 10 times 0. Okay. So let's simplify this a little bit. 5 dx dt equals negative 10 root 3, oh, ahead of myself, minus 10 root 3 equals 0. So 5 dx dt equals 10 root 3, or dx dt equals 10 root 3 divided by 5, which equals 2 root 3. And we're talking about the change in a distance, so we're going to say that this is feet per second. And so now we have answered our question, that the ladder is changing. The distance on the bottom is getting bigger, 2 root 3 feet for every second. Okay, so there we go. There's the whole problem. Let's go ahead and try a second problem. So, you and a friend are riding bikes to a restaurant, except you think the restaurant is east and your friend thinks the restaurant is north. You both leave from the same point, with you riding at 16 miles per hour east and your friend riding 12 miles per hour north. After you traveled 4 miles, at what rate is the distance between you changing? And so the east and north here is really important to help us come up with a diagram. So let's say this is your starting point, and you are going east, so you go a total of 4 miles. And your rate at which you're changing, your dx/dt, is 16 miles per hour. Well, what about your friend? Your friend, we don't know how far he went or she went, but we know that they're biking at dy/dt equals 12. And our question wants to find out what is dz dt, or the distance between you, and how is that changing. So it seems like we need to find a little bit more information here. Okay, I know that I can set up my derivative as x squared plus y squared equals z squared, and that when I take the derivative, I'll get 2x dx dt plus 2y dy dt equals 2z dz dt. And I also know that sometimes it's handy to cancel out the 2's. So let's see what we have and what we need. I know that x equals 4, so I can put x equals 4 there. And I also know that dx dt is 16, so I can put that there. I do not know my y, but it sure would be nice to know that. So this y I don't know, but if I could find it here, that would be helpful. And I know that my dy dt is 12, and so I can put that here. And if I knew my y, I could probably figure out my z. So that's something I need. And then I want to find the dz dt. So how do we do this? Well, I know from here that because I went 4 miles and I'm traveling 16 miles an hour, that I went for a quarter hour. That's how long I biked for. Now, if my friend also biked for that quarter hour, that means that he or she traveled 3 miles. So I have my y. And if I look at this, I've got a 3, 4, 5 right triangle. I know z is 5. And now I have all the numbers I need to fill in. So I'm going to write this as 4 times 16 plus 3 times 12 equals 5 times dz dt. And what I end up with is, once I solve for it, dz dt is going to equal 20 miles per hour. Okay, so we're going to stop this video here, come back for part 3 to see even more examples.